When an object is in static equilibrium, two conditions are satisfied. One, the forces acting on the object are balanced, and two, the torques acting on the object are balanced. Let's give an example. Here we have a table. This blue outline is the outline of the table, and we're looking down on top of the table. So we've got, you can imagine, two 2x4s that are sitting on a table, and we're looking down at them. If we apply forces in those locations, you can see that those forces are equal and opposite. So the forces are balanced on this object. However, this 2x4 is not in static equilibrium, and that's because the torques are not balanced. When these forces are applied, this object will tend to rotate, in this case clockwise, which means that this 2x4 is not in static equilibrium. On the other hand, if we take those same two forces and we apply them in this sense, they are equal and opposite, and there are no net torques on this 2x4. So this 2x4 won't go anywhere, nor will it rotate. Whereas the 2x4 on the left, while he won't go anywhere, he will rotate. So this object on the right here is in static equilibrium. The forces must be balanced and the torques must be balanced. Let's try an example problem. We have here a beam supported at the ends. One end is anchored in, that one on the left, and the one on the right is sitting on a roller, so that if the beam were to change length because the temperature changed and the beam would expand a little bit, this roller would allow the beam to do that. That's not important for this problem. We've got a point load of about 1,000 newtons that acts 3.2 meters from the left end, and we're asked to find the support reactions, which means we're asked to find the forces that are acting on the beam upward at the left end and the right end to hold the beam up. We're assuming that the beam's mass is negligible for this problem. So, for this beam to be in static equilibrium, the forces have to be balanced and the torques have to be balanced. So we're going to write two equations. Let's first write a force equation. If I choose up to be positive, Ra, the reaction at A, is acting upward, the reaction at B is acting upward, the 1,000 newtons is acting downward. So that's why the force equation looks like that. Now clearly that's not going to be enough to solve this problem because we only have one equation, but we have two unknowns, Ra and Rb. So that induces us to write a sum of the torques equation. Now, to write a torque equation, you have to choose a point somewhere on the object. And here, arbitrarily, I've chosen the left end. You can see I've got the little green dot there. And what we do is we sum the torques about that point. Well, reaction at A has no torque about that point because the lever arm for Ra with regard to that pivot point is 0. And if the lever arm is 0, then Ra has no torque effect with regard to that axis. So, the other two forces, the reaction at B and the 1,000 newtons, do have a torquing effect around this pivot point. So, the torque with regard to reaction at B is going to be that force times the lever arm, which is 4 meters. And if you can imagine force B pushing this beam, if this left end is fixed, you can see that the beam would rotate counterclockwise. And typically counterclockwise is taken to be positive, but it really doesn't matter. But I've used that convention here. The 1,000 Newton force, which is at a lever arm of 3.2 meters from that pivot point, would cause the beam to rotate clockwise. So it's given a negative sign. And those torques must add up to 0. So we're going to solve this second equation for the reaction at B because we have one equation and there's only one unknown. So RB turns out to be 800. Then we're going to plug that 800 newtons into the first equation, the force equation, so that we'll get RA plus 800 minus 1000 equals 0. Well, clearly RA is going to be about 200 newtons. Now, we've done this assuming that the beam's mass is negligible. If the beam had weighed, let's say, 600 newtons, are we in agreement that 300 newtons more would be needed on each end, if this is a uniform beam, to hold up this system? So we would get something like 1100 newtons for the reaction at B, which is 800 plus 300 more, because this 600 newtons would be distributed evenly between the two sides, and the reaction at A, instead of just being 200, would be 300 more than that, which is 500. So let's summarize. In this lesson we discussed the definition of static equilibrium, namely that an object must be in both translational and rotational equilibrium, and how to solve simple beam problems. And here's how you do that. You write a sum the forces equal to 0 equation. You choose a convenient pivot point where an unknown acts on the system, and then you write a sum of the torques equals 0 equation. You solve the torque equation for the missing variable, and then you plug that into the force equation.